What's up, guys? Here I'm gonna do a few more problems from the quiz today. Just a few of them that some periods we didn't get to cover all the questions that I wanted to go over. So I'm gonna do a couple of them. I'm gonna start with the one with the car. It's got a small car. I'm gonna call it small car SC, and it's got a mass of m. Speed is 2v, and it's going on a circular part of a track, along with the large car, call it LC, whose mass is 2m, and speed is just v. And the problem tells us that when they're going around the track, the smaller car needs a force of static friction F to not slip. And the question is, well, what does the larger car, what force of friction does it need so it also doesn't slip? So they're both going on the same track. So the R is the same for both. So radius is the same. All right. All right. So we know that if it's going in a circle, it's experiencing centripetal force. All right, circular motion. So we know that our equation for that is mv squared over r. All right. One of the many equations. We've gone over quite a few of them the last few days. So this is the one we're going to use because it's talking about mass and velocity. So this is the equation we're going to pick. And if we look at how these things change, the question is, what is the force? What force we need for the large car? Well, look at, if we compare the small car to the large car, their velocities. The large car velocity went down, right? It went from 2v to 1v. And what's the ratio of change? Well, it went down by a half, right? Got half as big. So we're going to say our velocity changed by a half, right? Or it got multiplied by a half, right? Half times 2 is 1. But our mass went up. Our mass went from just 1m to having 2 m's. So our mass changed by doubling, got 2 times bigger, right? So you might think, well, these kind of cancel out, right? But they don't, because of this little squared sign right there. Because the velocity was halved, we have to consider the fact that that number is being squared. So a half times a half is 1/4. So having the velocity actually decreases, is going to make us have 1/4 the force. But we also have to consider the fact that the mass did change also. The mass was doubled. So we take that 1/4 times 2, and we get 1/2, which tells us that the force then required for the larger car is going to be 1/2 of the original force F. All right. Again, this is a really good problem because it shows us just how these relationships can change the quantities that we're looking for. So the next one I wanted to talk about really quick was the one about we have a string, and it's hanging a mass of 10 kilograms, and it says that's the heaviest thing it can support. Now, if this thing has a mass of 10 kilograms, that means its weight is 100 newtons, which means the tension in the string is also 100 newtons. So the problem tells us that that's the maximum tension force that it can support. And then it tells us it's going to put the little box on with the same string, and it's going to twirl it around horizontally on a table with no friction, and wants to know what's the maximum speed that we can have. Well, we know the mass of the box is 10 kilograms. We know that the maximum force we can have before that string breaks is 100 newtons. So the force, centripetal force, is going to be 100 newtons. It's being caused by the tension force. And then we know that somewhere in the problem it told us that the radius was, it's not a 10 mass object it's a half a kilogram mass. Half kilogram for this part of the problem. And then the radius, it says, is 2 meters. We'll take this information, we're going to use the same equation we used earlier, and we're going to solve for what must the speed be. And I'm going to stop there because I don't want to just give you every answer, but I think you can just plug in the numbers here and should be able to solve for V. What should V be? And then the last one I wanted to talk about was the last one, and that is the one with the asteroid and the Earth. So it says that there's the sun, here's the Earth going around in this orbit, and then we have some asteroid, call it A for asteroid, and it's going around, and its radius of its orbit is twice that of the Earth, it says. So if we just call Earth's orbit, let's just say it's 1. Earth's radius is 1, right? Doesn't matter what 1 is, right? It could be 1 meter, 1,000 meters, 10,000 million meters, doesn't make a difference. Because again, it's about it's about the difference. It doesn't matter what the actual number is. It matters how it's different from the original answer, or how it changes. So its radius is 1, and its period, I don't know why I wrote it. Let me change the way I wrote that. The radius of Earth. And then we had the period of Earth is also 1, right? Well, that makes more sense, 1 year to go around. And then we have the radius of the asteroid is 2 times that of the Earth. So whatever the Earth is twice as far, right? So we just call it 2, right? And the question wants to know what is a period of rotation for the asteroid. So this is something a little new I wanted to introduce to you. You could use this equation. 2 pi squared. Oh no, it is 4 pi. Yeah, 4 pi squared. R cubed over. You could use this to solve this if you just made the mass, found the mass of the sun, or you could even just make the mass of the sun anything, because again, it's about how it changes. It's not about what the actual number is. But there's an easier way to do it I want to show you, and that's using Kepler's laws. Kepler has lots of laws about orbiting bodies and stuff, but one of his laws, his simple laws, was called, I think it's called the law of orbits, but it says that if you have 2 bodies that are both orbiting the same thing, then if you can set this ratio equal to each other, then you can solve for the unknown variable. So we have t squared over r cubed, and this is for the Earth, right? And that has to equal t squared over r cubed for the asteroid, right? So we know that the period of the Earth is 1 year, and we know that the radius of the Earth's orbit is 1 unit, and then we know radius of the asteroid is 2, and then so we can solve for t. So just be careful with the squared signs and the cubes. Of course, 1 cubed is 1, and then 2 cubed is going to be 8. But so just you can solve this. I think you can plug in the numbers here and then solve for the period of the asteroid. So this is called Kepler's law. Now it only works if both objects are orbiting the same thing. Right? So they're both orbiting the sun, so we can use Kepler's laws. If that wasn't the case, if the asteroid was orbiting something else, then it wouldn't work, of course, but it does in this case. So it's a little shortcut to remember, called Kepler's law. So there you go. Those are the 3 I wanted to go over with you. Don't forget, you can take this quiz, retake the quiz anytime before tomorrow, or anytime by tomorrow. I know some of y'all are working late, so y'all have a great day, and I'll see y'all tomorrow. Bye.